So today we are going to solve this paper, October-November 2020, paper 4. So the first question is define gravitational potential at a point. So we know gravitational potential at a point is the work done per unit mass in bringing a mass from infinity to the point. As we have discussed this earlier. So it's the so we consider the distance or the separation to be at infinity, and the energy is when we do work from the infinity to bring the mass from the infinity to this point. And another key point is that you have to write per unit mass, and the second point is for the bringing a mass from the infinity to that point. And you can also write the formula, which is the gravitational potential, which is this sign, equals to minus gm divided by r. And as this is an attractive force, you put a minus here. So moving on, the Earth may be considered to be a uniform sphere of radius 6.4 into 10 to the power 6 meters with its mass of 6.0 into 10 to the power 24 kg concentrated at its center. Okay, the satellite of mass 2.4 into 10 to the power 3 kg is launched from the equator. It is placed in an equatorial orbit at a height of 5.6 into 10 to the power 6 meter above the Earth's surface. Calculate the change in gravitational potential. Okay, now it's saying to calculate the change. So what we know is that for change, always we do this, like the potential energy final minus initial. So we already discussed the formula is this. So when we plug in it, plug in the formulas, what we get is if you take the common, then you get like after taking the common, taking the formula, the R common, R is common, you get R1 minus R2, like for this minuses, and just plug in the values, and note that the R2 that you're plugging in, it's also from the Earth, like again, like you have to consider the distance from the equator too. So note that, and the answer comes out to be 7.0 into 10 to the power 10 joules. So determine the speed of the satellite when in orbit. So what we do is we derive V by equating the centripetal force equation and the gravitational force equation, because we don't have a V here, do we? But if we like equate this, in a previous video I've shown you like how this has, like how the relation arrives, and you just substitute to get a V, and you make V the to get an expression in terms of V. So when you make V the subject and plug in all the values, you get V as 5,800 meter per second. Moving on, before the satellite in V is launched, its speed at the equator due to the Earth's rotation is 470 meter per second. So that is why the energy required to launch the satellite depends on whether the satellite in its orbit is traveling from west to east or from east to west. Of course it matters, because if you look, it's because there is a smaller gain in energy if the orbit of the satellite is in the same direction as that of the Earth's rotation. For instance, for here, like west to east. Or if you see otherwise, it will have to do extra amount of work to rotate in the other direction, right? Like if the satellite has to move on the opposite direction, so it's actually doing extra amount of work, right, which is not wanted. So moving on, so question number 2, what is meant by the internal energy of a system? So this is a very common question. So so it's the sum of the potential energy and kinetic energy. This is the first marking point. Of random motion of particles of a given system. Yeah, this is pretty basic, and this is a formula you have to memorize. It's coming often in the exam. And second, the atom of an ideal gas. So it's an ideal gas occupying a container of volume. It's a given at pressure this and a temperature of this. So they're providing also supply. Okay. The gas is heated at a constant pressure, so that this volume becomes this at a temperature T. So for the fixed mass of gas, calculate. So it's a fixed mass of gas, and we know it's an ideal gas, and we have to calculate the amount of substituent moles. So we have to use the PV equals to nRT formula, and we have to find the N. So ideal gas. We know that the ideal gas equation is PV equals to nRT, and when you make N the subject and substitute the pressure, the volume, the temperature, and the R, you get the substance, the mole value as this. So it's just it's pretty simple. So moving on, the temperature. So we know the pressure is constant, and when the pressure is constant, you can put this formula. I think we have learned this in O levels also. This is a very simple and a very basic formula. So when you make the subject, this becomes V2. This is the V2. This one is the T1, and this is the V1. So when you substitute all the values, from here, you get the T1. The temperature as this in Kelvin, by the way. It acts also for in Kelvin. Yeah. A2 you'll have to write in Kelvin. This is the rule. So during the change in B, okay, the thermal energy supplied to the gas. Okay, this is the energy supplied. Determine the work done on the gas during this work. So we know that work done is pressure divided by no, not divided by, multiplied by change in volume. We've learned this in AS also. So work done is, let's look at the solution. So we know work done is equals to pressure multiplied by change in volume. So all you have to do is just substitute. You substitute pressure and the change. This is the change. This one minus this one. So the change is. So the change is this. This is the final one. This is the final one, and this is the initial one. So all you do is you calculate the change, and you have the pressure which is constant throughout. You get a work done of 390 joules. But note here that I've discussed it in my another video that the work done here is for the expansion of volume. The volume has increased, so there will be a minus sign here. The reason I've discussed in another video, you can check it out. So it's negative because the volume of gas has increased or expanded, and vice versa if the gas compresses. If the work done is used for the gas, compression of gas, you will have a positive work done. So that's it. And moving on, determine the change in the internal energy of the gas. Okay, so the change using the law of thermodynamics, we get that the change in internal energy, which is delta U, is the thermal energy supplied, which is the Q, and the work done, which we calculated just now. So you just substitute the values, and here you go. This is the internal energy change. So moving on, A simple pendulum consists of a metal sphere. Okay, so there's a pendulum suspended from a fixed point by means of a thread. Okay, so it has a mass and it has a, this is a horizontal displacement and this is a vertical displacement. So the sphere of mass 94.0 grams. So this is in grams. We have to get, convert into kilograms. So this will be into 10 to the power minus 10 to the power minus 3. Is displaced to one side through a horizontal distance of this. We know this inside we have to convert it into 10 to the power minus 2 meters. And the center of gravity of the sphere is vertically. Yeah. So these are given in the pictures. The sphere is released so that it oscillates. Okay. So it goes like this, it's oscillate. It comes back to the same point, so it's called oscillation. And the sphere may have be assumed to oscillate with simple harmonic motion. So what is simple harmonic motion? So if you look into this, so it's a motion. You can write it in two ways: motion of an oscillator in which, or it's a type of oscillation in which the acceleration of a body is directly proportional to its displacement. So this acceleration is directly proportional to displacement. But this is the first marking point, and the second marking point is but it acts in the opposite direction. This is the second marking point. So the first one is important, that that acceleration is proportional to the displacement. I've discussed it in the oscillation chapter video. You can check it out. So when you just equate it, you get a proportionality constant of this, the angular frequency. So moving on, state the kinetic energy of the sphere when the sphere returns to the displaced position shown in figure 3.1. So this is the position when it returns to this. Oh no, to the displaced position shown in figure 3.1. Oh, so it was this and it has displaced to this. So here, momentarily, what we can see is after the next stage it will return back, but momentarily we can as it reaches up, momentarily what we see is the v becomes 0, right? So if you look at my answer, so at next point it will be instantaneously at rest. Yeah, so that's what I was talking about. And the kinetic energy is 0 because as v is 0, it's half mv square and v is 0, so you get 0 joules. So continuing, state the total kinetic energy. Okay, so the total kinetic energy is the no, the total energy. This is the total energy. So the total energy is all the kinetic energy and the potential energy. But the thing is here, it's at the top, so it must have all the energy. All the energy it has must have converted to the gravitational potential energy as it has gained height. So if you look, yeah. So the total energy at the top will be all the Ke, or the kinetic energy, will be transferred to the potential energy, because it is at the max height. And so total and we also know the vertical height, and like let's continue. Like, so the total energy is total gravitational potential energy, and if you substitute, and the formula goes like mass into g into h. So if you substitute, we know the vertical height as what, 0.9 into 10 to the power minus 2 meters. So we just substitute that, and we know the g, and you also know the mass here, mass. So by substituting, we get the total energy is this. So here's the joules. So that's 8.3 into 10 to the power minus 3. Moving on, use your answer in 2, okay, to show that the angular frequency. So what you have to do is, of the angular frequency of the oscillation of the pendulum is 3.3. We have to prove this. So So if you look like at the top, I mean, so if you look at this, like the total energy will be like, let me draw it. So it's moving from here to here and here to here. So when it like when it starts from here and it comes to this point, so it has a maximum velocity. So that's the, I mean, that's all the kinetic energy. That's the maximum kinetic energy it has. So this is the initial. I mean, we know that uh, the total energy during the oscillation is half mv square, and the v here you should take as the initial velocity, which is the starting velocity, because we know at the top, I mean at the top, like I mean at the, I mean let's look at it. At the top the v is 0, and we know that there is no kinetic energy, and you have to if you have to work with kinetic energy, we have to take the v, like the v naught, the v here. So so the first one is this, and the second one is this. There is a little, now we have to also bring angular, I mean relation here also. So we have to bring an angular relation, the angular frequency. So we also know that the relation between the linear and the angular velocity goes like this. The velocity is the angular frequency into the distance, I mean the displacement. So if you just substitute it over the v, so this v, we just substitute it, so it goes as this. We know the electric, uh, we found out the total energy as this, and the total energy can be found out in both ways, and in terms of gravitational potential energy, also in terms of the maximum kinetic energy. So we're using this now, like to bring, I mean, why are we using this, the kinetic energy formula? Because we want the angular frequency relationship to come in this formula. So we can do this by bringing v here, and we can bring v by using the kinetic energy formula. So all you have to do is substitute, and you get the angular frequency as 33.3 rads. And the maximum displacement, sorry, I forgot to talk about, is the horizontal distance traveled, which is 12.7 into 10 to the power minus 2. Yeah. So that's pretty simple and basic. Moving on. The period t of oscillation of the pendulum is given by the expression. I mean, we got this formula also in like O-level practicals. We usually saw this formula. Like you might have also come across the formula too. And so what it says, coming back to the question, the period t of oscillation of the pendulum can be given by the expression okay, and where g is the acceleration of free fall and L is the length of pendulum. Yeah, we also know this. So use the data from B to determine L. So now what you have to do is, like as we already know, so like we have to use the angular relationship, like we have to do something to bring the angular relationship back again, as we have to find that, because we don't know the time, and so how will we find L? I mean, then there will be two unknowns. But what we know is that we know that the t has another relationship. The time, the t period in terms of angular frequency, we know that is 2 pi divided by omega, and t pi divided by the angular frequency, and we have already found the angular frequency initially. So it's 3.3 rads. So if you could substitute, you'd get the time, right? So you could easily get the L by substituting all the values. So this is what we do. So we do t equals to t. So this is the linear one from the pendulum, and this t comes from the the angular frequency you will get it in the centripetal motion chapter. So we did this, we did t equals to t, and we got the omega, we found out the angular frequency. So we know the pi value and we got the time, and now all we need to know is the L. So the L comes out to be 0.990 meters. So the L comes out to be 0.90 meters. Moving on, state two advantage of the transmission of data in digital. So this is pretty simple. In your book, you will have lots of advantages given, and among them, the points could be signals can be regenerated. Yeah. Secondly, signals can be encrypted. You could send secure signals through digital data. So you have to write only two, but for knowing purpose, I've mentioned two more. So the signals can be checked for error, and digital data can be transmitted at a greater rate. Yeah. So moving on, an analog signal is to be transmitted in digital form. Okay. The transmission system may be represented in blocks from analog to digital convert ADC. So it's converting analog back to analog using this to convert circuit. Okay, so this is a transmission system. So the variation of time t of part of the input analog signal is shown. So this is the input analog and the time here. The analog signal is sampled at the time interval of 10 milliseconds. The first sample is taken at time 0. Some values of the sampled analog signal and the corresponding digital signal are shown in table 4.1. Each digital number is contains the 4 bits. So this is so the table shows per time interval how much what's the analog signal. So it's the interpretation of graph also. So like if we see at time 0.2, the analog signal is 6.2. So at 0.2 we do get around 6.2. Yeah. So what we'll have to do is just use the graph to 0.30. You just use the graph to get the value. So I've done it accurately in my as I've printed the question paper. So so you just have to match up the values from graph. So this comes out to be 3 and this comes out to be 4.8 and the last one is 1.0. So if you look at 0.5 seconds, so 0.5 milliseconds, the value comes out to be around 1. So there you go. So you just have to match up the values from the graph, and after you have done it, like 3.0, 4.8 and 1. So all you have to do is convert this numeric data into digital signals. Into digital data. If you have computer, if you have taken ICT or computer science in your studies, if you have taken then, or if you had taken, then you may know how the binary conversion works, and you will also learn this in A2. You have learned in A2. So I have a separate video of how the conversion works. So you just have to convert these values to binary. So underline the least significant digital for the time of 0.2 milliseconds. So we have to find out, underline the value of 0.2 seconds. So So what you have to do is at 0.2 seconds you have to show out the value, like how has it. My one is not straight, but you have to draw a straighter one and show that the value is 6.2 here. Yeah, we get 6.2, and we did complete the table. So a single bit from the output, a digital analog converter, corresponds to the output analog signal from one signal of 1 millivolt. Assume that the conversion and the transmission do not introduce a time delay on the axis. Show the variation with time t of the output from the digital to analog converter. So now what you gotta do is, you have found out the the corresponding value of the time. So at time 0.1, what you get is, you get a signal of 5.7. So here's the trick. What you do is, you get rid of the decimal and just take the 5 and you put a reading at 5. So what you do is, from 0.1 we got a reading of 0.5. We got a value of 5, so you go up to 5 and you get a continuous value of 5, and again it changes at 0.2, which is 6. You get rid of this 0.2 and just write 6, and so it's 6. So like that you just draw the graph as I've shown here. So let's continue. So question 5, what is meant by a field of force? So it's not talking about any specific force like electric or gravity. It's just talking about field of force. So what is that? So it's a region of space where a particle can experience a force. So what happens is, it's pretty simple. So what it says is, it's a space where you will find fields, like it can be electric fields or gravitational fields, and for that fields you will experience a force. For instance, if you if it was electric field, and if you kept a charge here, so the charge would experience a force. And for instance, if it was gravitational field, so let's say it was gravitational field and attractive force. So if you put another mass, we know there is attraction force acting. As there is interaction of force working. So that's it. Moving on. State one similarity and one difference between the electric field due to a point charge and the gravitational field due to a point mass. So as we know that the formulas are almost same and the principles are almost same. So we both know, we know that for both the electric field and the gravitational field, both decreases as the distance increase. So the first point is both decrease with distance. Let me just erase all other things. And also they don't just decrease, but they decrease at the square of the separation. So both follow inverse law, and the third one is both are radial. Because if you see, if a mass attracts, or if there is gravitational field working, it works radially, like as you see, it's radial. So moving on, the differences. So as you can already say that gravitational field always acts towards the center of the mass. This is the prime difference. But what electric fields can do, if it's plus, if it's minus, so it can act, we can see it can whether act in towards or away. So that's the main difference. So gravitational field is always attractive in nature, whatever I wrote. Gravitational field is always attractive and it's towards the mass, and whereas the electric field can be both towards or away from the charge. So moving on, an isolated solid metal sphere. Let me just erase it. So an isolated metal sphere of radius 0.5 meters is situated in a vacuum as illustrated. Okay, so it's in a vacuum. The electric field strength at the surface of the sphere is, so the electric field strength is already given. All you have to do is find the charge. So we know the electric field formula, that is charge divided by 4 pi epsilon into the distance square and the radius square. So you just plug in the values. We know that electric, it's already given, which is 84. So this is the electric field, and you just you just substitute the values and the distance, and we know the R is 0.15 meters. 0.15 meters. You just follow the formula and get a charge of 2.1 into 10 to the power minus 10. So 2.1 into 10 to the power minus 10 is my charge in coulombs. The electrical field strength at point P, a distance x is equal to 0.45 meters from the center of the sphere. So what is the electric field strength? So we know that, oh shit, how do I now make this? I'm sorry guys, that's a mistake I've done. So I hope you can manage it. So we know the electric field. So how can I make this straighter? Can I make this straighter? So let me just spin down. So how do I rotate? So yeah. So the main formula you'll have to use is this. But to understand this, let me show you something. So we know that electric field is one. So what you see here, that the R is inversely proportional to the electric field. So at point P, the distance will be inverse. So the relationship is inverse, and same for the point S. So the ratio comes out to be like this. As the radius is, the relationship comes out to be like this. It's inversely, but it's squared also. So for P, you get a distance of P. For S, you get the radius as S, and there is a square. So as a relationship, as a ratio, you have to put the square, and for P, you get inverse this, and for S, inversely, you get here. So you just plug in the values, and you get the electrical field strength as 9.33. 9.33. Moving on, using information from B, okay, to show on the axis the variation of the electric field strength from distance x from the center of the sphere for value x from x0 to x. So let's look at the solution. So there are two parts, like up till to the middle of the, So the graph starts rising from here, because up till this much, all the charge is within the surface. I mean, it's retained within the surface, so there is no electric field. But later the graph follows. I mean, it rises up till 8. We have found the what? So it rises up to 84, and the relationship it follows, it decreases, but it decreases like at the inverse square relationship, because it's 1 by r squared. So it decreases, but it decreases at like this. So we know like the inverse relation is it comes out to be a curve like this. So as this also follows the inverse relationship, so it's gonna be like this. The second part, it will decrease, but like this, and it will keep on going. So moving on to question 6. Define the capacitance of a parallel plate capacitor. So the capacitance is it's the ratio. So the first marking point is this, that it's the ratio of magnitude of charge, I mean the Q, on the plate, and the potential difference, the V. So, or you could write the formula between the parallel plate. So that's it. Moving on, state 3 functions of capacitors in electrical circuit. So it has a lot of function, as we know. It can act temporarily as a battery, and it can also it can act it can also have a smoothing effect. I mean, if you have seen the bridge rectifying circuit, you will see that when AC is converted to DC, what happens is they are not smooth, and what capacitors can do is that they can, I mean, fill in the gaps, or the voltage that is missing. So if you look at the answers, so it acts as a temporary power supply. We say this. It is used for blocking DC, and it can be used as an oscillator. As I said before, it can also be used for smoothing the current, usually in rectifiers. So moving on, a student has available 3 capacitors, each of capacitance 12 volts. So he has 3 capacitors, identical capacitors, each with 12 microfarad capacitance. So the question is saying that you have to draw a circuit diagram using the 3 capacitors in such a way that the total comes out to be 18 microfarad. So what we know is when it's in parallel, the capacitance adds up, and when it's in series, it decreases. It's kind of like the opposite of resistance formula. So for making 18, what you can do is put 2 of the 12 microfarad capacitors in series. So what we'll do is, so our main goal is to make 18, right? So putting the 2 in series halves the capacitors, as I've already said, and as I already told. I mean, it's the opposite of the resistor formula. So in resistors, what you did was we could add. I mean, they added up, but here the capacitance actually gets divided. So the the capacitance is now 6 microfarad, and like how it halves and how it is discussed in my tutorial video. And so in series we got 6 microvolts, and when the 6 and 12 are 12, they are in parallel. So in parallel, the capacitance adds up, as I already said, So if you add up 6 microfarad and 12 microfarad, you get 18 microfarad. So we just fulfill the we just made the output 18 microfarad. The capacitance in total, like we just so in the next one you should put it in such so that you get 8 microfarad. So what you can do is we have to decrease it. So first you put it in parallel. So 12 microfarad and 12 microfarad in parallel gives you 24, and the other one you will put it in series. So now the series, now the 24 and the 12, they are in series, the capacitors. So now the capacitance that you will calculate, you will use the formula, you just multiply both and add divided by the addition of both. So you get 8 microfarads. So that's it. That's it for today's video, and we'll proceed on to the next questions in a later video. So up to now, that's it, and see you next class. Bye. Bye.